All right, so we are on chapter 9, section 4, and we're going to talk a little more detail about weak acids, excuse me, and bases. Remember, weak acids and bases are those that don't dissociate 100% in solution. And so just like we were able to find a K value for an acid-base reaction, a strong acid or a strong base, we can do the same thing for a weak acid or a weak base. And so it's the same thing. K is still equal to our concentration of our products over the concentration of our reactants. So if we look at trying to write this equation for what we've given here, right? What do we have here? Well, here are our products, and here are our reactants. And remember, when we're writing these equilibrium expressions, if it is a liquid or a solid, we don't write it. So we're not going to write this liquid when we put it in the equilibrium expression. And y'all know that they go back and forth between drawing the structure a little bit and writing just the molecular formula for some of this stuff. And so you just have to remember that COOH, remember we talked about this before, really means that you have a carbonyl carbon that's bound to an oxygen, right? And so what you see here is the same thing as this, okay? So just kind of be aware of that. I'll try not to do that to y'all. But so you'll only have one thing in the reactants at the bottom, right? Because water is not a part of this. And then you have two different things, right, on the top. So one here and one here, one here and one here, right? So it works exactly the same as we have written a K before. So all weak acids are going to disassociate a little bit. And they're going to do that by getting rid of that hydrogen ion or that proton, right? And that proton can disassociate and it can form a hydronium ion, right? And so we give a value to that dissociation constant, right? The concentration of the undisassociated to the disassociated, right? So this is the disassociated and this is the undisassociated. And we're going to get a K. But because it's an acid, we don't just call it a K, we call it a Ka, right? It just means an equilibrium constant for an acid. That's all it means. It's not a big deal. So when you do this, if it's a weak acid, you're going to get a really, really, really tiny number. Not negative, but really, really small. So less than 1 and really, really small. So the weaker something is, right, the smaller the dissociation constant is. So water is a very, very weak acid. Hydrogen sulfate ion is a stronger acid, right? And don't worry, if I ask you for a Ka value, I'll give you a table. So for all weak acids, the Ka is going to be less than 1 because it doesn't disassociate, right? K is our products over our reactants. And we know that our reactants are going to stay together. So you're going to have more reactants. And so our Ka value is going to be less than 1. So that tells us that when we have more, for example, acetic acid molecules, then when the hydrogen comes off and makes an acetate ion. So because all weak acids can reach that equilibrium in solution, we can give a Ka value for a particular temperature. Now temperature will change the Ka values, but that's okay. We're just going to stick to a given temperature. And we know that each different compound or each different acid is going to disassociate to a different extent. So some disassociate more than others. And so they'll have unique Ka values. So the larger the Ka, the stronger the acid. So this is a larger Ka and stronger, this is a stronger weak acid. And this is a smaller Ka and a weaker weak acid. They're all weak acids, but some of them are stronger than others. Why couldn't we have used a different word? I don't know. All right. Okay, so for example, if we look at some of these, we talked about our functional groups that are charged, right? So we had a carboxylic acid. We know we can have a carboxylic acid and it can lose this hydrogen. This hydrogen can go hang out with this water, and we can make a carboxylate ion, which is charged, which is negative, and we can make a hydronium ion, which is positive, right? The same thing, not the same thing, but a similar thing can happen with our protonated amine. Our protonated amine is already positively charged, and it can give up one of its hydrogens to water and form an amine, which is one less hydrogen attached, and that hydronium ion. So whenever we talk about weak acids and them giving up hydrogens or gaining hydrogens, what we call them are the acid and the result of losing that hydrogen. If you're an acid, right, you're going to donate a proton. So if you donate that proton, what's left of you? That is what's called the conjugate base. Because remember, the reaction can go in the opposite direction. And so if we go in the opposite direction, we're going to go from being negative to gaining that proton and becoming neutral. So that would be acting as a base. But we always look at the forward direction and say the things that are in the reactants in the forward directions are either acids or bases. And then the things that are in the products are the conjugate acid and the conjugate base. And so it's basically like the before and after, the before and after. So if you look at water, what happened to water? Well, water picked up this hydrogen and attached it on there. So it started off as a base because it was an acceptor. It was a hydrogen ion acceptor. And so then it turned into H3O plus, which is a conjugate acid. Because now that you're H3O plus, you could, in essence, give up a hydrogen, right? So that's just how we look at them. We look at them so that we can see what happens in a forward direction and what happens in a reverse direction, right? And so we call them conjugate acid-base pairs. And the only difference between a conjugate acid-base pairs is the loss or gain of one hydrogen ion. That's it. That's it. So we usually write weak acids in general as whatever the formula of the acid is plus an H. And then the ion is the ion form without the H, and so it is negatively charged. So we call the acid HA, and we call a conjugate base A minus because that's the ion. So if you look at the amine, on the other hand, the amine is going to be the one that accepts a proton from water. So if it's an acceptor, it's acting as a base. And so once it accepts it, then it becomes an NH3 plus, and we call that the conjugate acid. Water, on the other hand, is going to be the one that is going to donate, in this case, the hydrogen ion to the amine. And so we end up with an acid, water being an acid, and then the hydroxide being the conjugate base. We'll look at some practice, right? So remember, the conjugates are always going to be on the product. So regular acid and base and reactant, conjugate in the product. And then whenever you donate a proton, the conjugate base is just going to lose one positive charge or gain one negative charge, however you want to think about that, right? And so you're going to change by only one charge. And the total charge of the reactants must equal to the total charge of the products. And so we'll look at some examples of this. This is really important in terms of controlling acid-base equilibria inside of our bodies, right? Inside of our red blood cells, we have a protein called hemoglobin. And hemoglobin carries oxygen, like you take a deep breath in, oxygen's in your lungs, the oxygen moves to your bloodstream, where it's picked up by the red blood cells inside of your, picked up by the hemoglobin inside of your red blood cells. And then it brings it all over the body, right? So you have both protons and oxygen that bind to hemoglobin, but it's really with opposite affinity. So you can only carry one or the other. And so if you change the concentration of an acid or change the concentration of the oxygen gas, you're going to actually shift your equilibrium, and it allows you to balance the amount of oxygen that you want in your bloodstream. It's kind of a cool cool way that your body regulates that. Okay, so let's go do a few quick problems. All right, so these are things that I would give you. What are the common strong acids? And I would give you some values. I might not give you this arrow right here. That might be something I don't give you, but I would give you the table, right? And you have to remember that all these dissociation constants, that's what Ka is. It's a dissociation constant of an acid. They're all weak acids, so they're all gonna be less than 1. But you just have to remember, what is K? K is my products over my reactants. If you can get that in your mind, you'll be okay. All right, so using the tables, identify the stronger acid in each pair. So what I'm gonna do is H2PO4. Here's my H2PO4. So all I want you to do is write down its Ka, 6.6 times 10 to the minus 8, and then HPO4. So then, come on, HPO4 2 minus right here. So this is 1 times 10 to the minus 12. So which one is stronger? The one that has a larger Ka value is stronger. So this one has the larger Ka value. So this one is stronger. And I guess I should have kind of stuck to the color. This one is stronger, right? Okay. Let's see. HF, where's HF? HF is right here. And HCOOH. All right, let's do red. HCOOH, right? So which one is going to have a, which one is going to be the stronger acid is the one that is going to have the higher Ka value. So it's going to be right here, HF. So let's circle that one in blue, HF, right? HBr or HNO2. Now, this one should ring a bell. I bring clay, HBr. That's a strong acid. HNO2, you only have 1 hydrogen and 2 oxygen, so that means you have 1 more oxygen than hydrogen. This is weak. This is a weak acid. So which one's going to be stronger? You don't even have to go to the table. HBr is going to be stronger, okay? All right. Identify the acid base on the reactant side of the following equations and identify the conjugate acid. All right, I'm going to tell you my little trick. If there's water, I like to do water first because it's easy. And then it tells me what the other ones are, okay? So I'm going to first look and I'm going to say, okay, this is what water was and here's what it's turning into. So if I'm H2O and I turn into H3O+, I have gained a proton. I am an acceptor. So what is an acceptor? That's a base. And I'm going to turn into my conjugate acid, okay? So a lot of times I'll just write B and I'll write conjugate acid, Ca, just so that we can fit everything in. Okay, so now HSO4 minus is turning into SO4 2 minus. So I've lost my hydrogen, right? I've donated my hydrogen. If you donate your hydrogen, what are you? You're an acid. A lot of times I just abbreviate that A. And then I'm going to make my conjugate base. Let me write it out this time. Conjugate base, okay? So that's all you have to do. If you could do water first, it really kind of helps. It really makes it a lot easier. So here I got my water, turn it into hydronium. So that tells me that water is acting as a base because it is going to accept a proton. So this is going to be my conjugate acid. Remember, whenever you have a pair, you have a base, an acid and a base, or a base and an acid, right? Okay, so now my NH4 plus to NH3, what happened? I lost a hydrogen here. So this is going to start out as an acid. We just call it an A, and this is going to be my conjugate base. Okay. All right. Ooh, I have no water, so I kind of need to think about this one. So one thing I notice when I look at this is that I see cyanide, I see CN. So I'm going to kind of want to follow my CN and see what happens, because I know that's a polyatomic. So here, all right, so I go HCN to CN minus. What happened? I lost an electron. So an electron, a proton. So that this one must be the acid, and this one must be the conjugate base. All right, now what's happening with my other stuff? I got NO2 minus going to HNO2. So my NO2 minus is going to be the base because it's going to accept a proton, and the HNO2 has the hydrogen, so it could donate it. So that would be the conjugate acid. Okay, not too bad. All right. Write the formula and name of the conjugate base formed from each of the following acids. Okay, so we're told that we're starting with an acid. So if you have an acid, what is going to happen? The acid is going to donate. Here we go again. We're going to donate. Oh, I kind of want to get it right. We're going to donate a hydrogen ion, okay? Which means we're going to get rid of, like if you donate something, you give it away, we're going to give it away, okay? So what are we going to make when we lose the hydrogen? Well, that hydrogen comes with a positive charge, so be very careful that you name the ion correctly. So this is F minus, so this is fluoride, FLUO, fluoride, right? So it's the fluoride. And you can write fluoride or you can write fluoride ion. Either way, your homework accepts both. I double checked. All right, so what happens in B if we have H2O, which is really HOH? What happens if we get rid of a hydrogen? We are going to form OH minus. We know OH minus is hydroxide, TROXIDE, hydroxide. It's on your polyatomic ion chart, I do believe, right? H2CO3, you're going to only lose one of those hydrogens, right? And what are you going to end up as? You're going to end up as H, because you're going to keep one of them, CO3 minus. And so if you look that up on your polyatomic ion table, which of course you will have on the exam, you get bicarbonate, right? Okay, D, HSO4 minus. We're going to lose this. Now look, we already have a negative. So if you already have a negative, what's going to happen is you're going to have one more negative. So we're going to be SO4, but be careful, one more negative is 2 minus or minus 2. So if you go look on your polyatomic, this is sulfate, okay? All right. Okay, so we named our conjugate base formed from each of the following acids. So all of the things that we wrote here, all of these are conjugate bases. So they're what's left when this acid, here these are our acids, lose their hydrogen, okay? So let's kind of switch gears. Write the formula, name the conjugate acid formed from each of the following bases. So in this case, here are our bases. What are our bases going to do? Our bases are going to gain a hydrogen ion, right? So let's think about what happens. Now you need to go and look at your polyatomic ion table and see what these polyatomic ions are. CO3 2 minus, that is called CARBONATE, that is carbonate. So if you go from carbonate, remember I went to chemistry class and I got atic-itis. So if I was ATE, I'm going to become IC. So this is carbonic acid, right? Formula and name, carbonic acid. All right, H2O, this is water, right? What's going to happen to water when it gains a hydrogen? If you're going to gain a hydrogen, oh, I think I had to write the formula. I'm sorry. Formula for a carbonic acid, right? Just add a hydrogen, CO3. Now, if you added a hydrogen, what happens to your charge? Your charge goes to -1 because you gain that positive hydrogen. Okay, H2O. If we gain a positive hydrogen, what are we going to form? We're going to form H3O plus, and we call that hydronium. That one you have to know, hydronium. Okay, H2PO4. If you go look, I believe in your polyatomic ion table, they name this dihydrogen phosphate. And it's fine. It's fine. I'm not going to give you one of these, but let's just draw it. It would be H3PO4. Now, what would happen to that charge? That charge would go away, right? Because you're adding a positive to it. So H3PO4 is really phosphoric acid. And the naming rules aren't always perfect. And so I don't understand why they give you examples that are not quite perfect, but anyway, okay, Br minus. How many times have we done this? Br minus, right? If we're going to add a hydrogen, so that's HBr, right? And it's binary, so this is going to be hydro, bro, but it's not going to be bromide. It's going to be IDE to IC, hydrobromic, PRO. Ooh. Oh, come on. Mic acid. Hydrobromic acid. So just keep that in mind. Okay, I think that is it. Oh no, we have one more. Okay, complete the following reactions and identify the conjugate acid-base pairs if the named reactants act as an acid. Okay, formic acid found in ants and bee stings. Okay, so what's going to act as an acid? This one. Here's my acid. So what's going to act as the base? My water is going to act as a base. So what's going to happen? If I have an acid, it's going to donate a proton. So I'm going to be HCOO minus, right? Because I'm not going to put my hydrogen. I'm not going to put that. And then this is going to be my conjugate base. And then I'm going to make also, my water is going to gain a hydrogen. And so I'm going to make H3O plus. That's going to be aqueous, and this is my conjugate acid, right? What does it say? Complete the following reactions, identify conjugate acid-base pairs if the named reactant acts as an acid. There you go. Okay, so we're good. Sometimes I gotta go back and read all the instructions. All right, H2PO4 minus, dihydrogen phosphate, a component of cell buffering system. All right, so what's gonna happen? We're telling us that the dihydrogen phosphate is gonna act as an acid, so my water is gonna act as a base. Sometimes I like to do water first because it's sort of easy. So if it's gonna be a base, it's gonna accept a hydrogen, so we're gonna have H3O, and it's gonna be a plus, we're gonna put it aqueous. Now my acid is the one that's going to lose a hydrogen, but only one. That's gonna be HPO4 2 minus. So this is going to be my conjugate base. Did I write this? Conjugate acid, right? So you have a base and a conjugate acid, and you have an acid and a conjugate base, okay? Bicarbonate, a component in blood buffering systems. All right, so you have HCO3 minus. This one, I guess I shouldn't give that away so quickly, but what happens if you have water, right? And bicarbonate, a component in blood buffering, what you're told here is that this is acting as an acid. So then my water has to be the base. So if I'm going to make a conjugate acid with water, excuse me, right, I need to get H3O plus because the base is going to accept that hydrogen ion. It's aqueous. And then I'm going to lose my hydrogen. I'm going to make CO3. Now be careful with my charge because I lost a hydrogen, I'll be a -2, okay? So, oh, and this is my conjugate base, right? Acid, conjugate base, base, conjugate acid, okay? All right, that is it. And y'all have a great rest of your day.